Hey guys, thank you for tuning in. This video is on one of the most important concepts related to single phase transformer, the phasor diagram. It is one diagram which can give you a relation between all important parameters associated in the circuit. This video today is going to be a step-by-step explanation for how each parameter and its vector is drawn. So make sure you watch it till the end. Earlier on explanator, we saw the equivalent circuit and working of a single phase transformer. I highly recommend you watch it before starting with the phasor diagram, mainly because the assumptions considered there are valid for drawing this diagram as well. With that prerequisite, let's begin. Consider the circuit diagram for a single phase transformer connected on an inductive load. Let's quickly list down the parameters which are to be drawn on this phasor diagram. Starting from the secondary side, you have a total of 5 terms. The first one is V2, which is the output voltage drop. Next is I2X2, the drop due to magnetic leakage flux in the secondary circuit. I2R2, drop due to winding resistance in the secondary circuit. I2, the secondary current, and E2, the induced EMF in the secondary winding. Then there is this flux phi in the core which links both the primary as well as the secondary circuit. Coming to the primary side, you have a total of 9 terms. Starting from the end, there is E1, induced EMF in the primary winding. I2 dash, the primary current to neutralize the demagnetizing effects of I2, Im, the magnetizing current, Iw, the working current, I0, no load current, I1X1, drop due to magnetic leakage flux in the primary circuit, I1R1, drop due to the winding resistance in the primary circuit, I1, the primary current, and last V1, which is the input source voltage. So on the whole, you have a total of 15 terms which are to be drawn on this single phasor diagram. To start with, you draw a reference line. Now this line represents that one parameter which is common to both the primary as well as the secondary circuit. It is evident looking at the circuit that this term has to be the flux phi. So call this reference line as phi. One parameter drawn, 14 more to go. The second term to be drawn should have some relation with this reference line phi. The terms are drawn from the output end, and with that convention, V2 has to be drawn. Using KVL in the secondary circuit, you get V2 equals to E2 minus I2R2 minus J times I2X2. As can be seen from this equation, there is no direct relation between V2 and phi. So you cannot draw V2 right away. You have to draw the 3 terms in that equation and later add them up to get to V2. But however, according to Lenz's law, E equals minus d phi by dt. If the flux flowing in the transformer core is given as phi equals to phi m sine of omega t, then the induced EMF E can be written as minus of omega phi m cos of omega t. Rearranging the terms in sine form, you will get omega phi m sine of omega t minus pi by 2. When sine attains its maximum value of 1, the equation will attain its maximum value of Em equal to omega phi m. Therefore, the EMF equation may be now written as E equal to Em sine of omega t minus pi by 2. Comparing both these equations, you see that E lags phi by 90 degrees. So you can draw E2 with reference to phi as lagging by 90 degrees. It points in the minus y direction. To plot the next 2 terms of the equation, which are both potential drops, that is minus I2R2 and minus J times I2X2, you will need to know the position of current I2. In the secondary circuit with the voltage source as E2 and inductive load of ZL, The secondary current I2 will lag E2, draw I2 according to this. The potential drop I2R2 across the resistor R2 will be in phase with the current I2. But the equation needs that minus I2R2 has to be drawn. For that, reverse the direction. This vector has to be added to E2. So shift this vector to where E2 finishes. The last term in the equation for V2 is minus I2x2. To draw this, take help of the impedance triangle. According to this, in an inductive circuit, X leads R. You therefore draw minus I2x2, 90 degrees leading the vector minus I2R2. Since the direction of current has already been reversed, you need not worry about the minus in minus I2x2 again. With this, all the parameters in the equation for V2 have been drawn. You can add the three phasors to get the resultant vector V2. The first vector, that is E2, started at the origin, and the last vector, that is minus I2 x2, has finished at this point. Join the start and the end points to get the resultant vector V2. The phasor diagram for secondary circuit has now been drawn completely. Moving over to the primary side, the first vector that has to be drawn is E1. Draw it the same way as E2, that is in minus y direction. But the only difference that you will see here, that E1 has been assumed to be lower than E2. So the length of E1 will be slightly smaller. The next terms to be drawn are all interlinked to each other. They have a relation as shown in these three equations. Looking at these three, you will see that the first equation cannot be plotted at the moment because it involves the terms with I1, which is not yet been drawn. The second equation is for drawing I1, but that itself is a vector sum of other two terms. So unless you draw them, you cannot proceed to drawing I1. Coming to the last equation, it has two terms, Im and Iw. In this, Im is the magnetizing current which creates the flux phi. Hence it is directly related to phi. So Im is drawn along phi. To draw the second term, that is the working current Iw, you see in the circuit diagram that it flows in the resistor, while the previous current Im flows in an inductor. From this, you can say that they have a phase difference of 90 degrees. So if Im is plotted along phi, Iw will have a phase difference of 90 degrees pointing in plus y direction. The vector addition of these two will give you a resultant of no load current I0. Coming to the second equation again, I0 has been drawn and only I2 dash is pending. You can see from the relation shown in the bracket that I2 and I2 dash are in antiphase, which means to get I2 dash, all you have to do is reverse the direction of I2. So reverse this vector I2 and add it to I0. The resultant of I0 and I2 dash will give you primary current I1. Coming to the first equation, for drawing V1, we need E1 and the other two voltage drops. Out of these three, E1 has been drawn already. But if you add the other two voltages, that is I1R1 and I1X1 to it, the resulting diagram that you get will not satisfy these equations. That is why you tweak the diagram slightly such that it satisfies the equation which is governing it. I'll definitely do a video on this concept in depth real soon. For now, the tweak is that you take E1 and shift it upwards. When you do this, you have E1 with a negative sign. The magnitude of E1 remains the same. The next term in the equation is I1R1. It is a resistive drop, hence it will be in phase with I1. Shift it and add it to minus E1. The last term in the equation, I1X1, is to be drawn using the impedance triangle just like in the previous case. So I1 x1 goes 90 degrees leading I1 R1. The origin is where the first term, that is minus E1, was drawn, and the last term I1 x1 has ended here. Join the start and the end points to get the resultant vector V1. The angle between the input voltage V1 and the input current I1 is phi1, and it gives the primary power factor of the transformer as cos phi1. The input power to the transformer is hence V1 I1 cos of phi1. The secondary power factor of the transformer is cos phi2, and the output power of the transformer is V2 I2 cos phi2. The angle between the input voltage V1 and no load current I0 is phi0. You can clearly see that phi1 and phi2 are not the same like that in an ideal transformer, and it is also seen that V1 leads I1 and V2 leads I2. Thus it confirms that the diagram is correct because V has to lead I in an inductive circuit. This is how you draw a complete phasor diagram for a single phase transformer on an inductive load. In the coming videos, I'll do the resistive and capacitive loads as well. Do drop in your feedback and suggestions, and don't forget to like, share and subscribe to Explanator, where every solution has a simple explanation.